Friction is another thing we can analyze using static equilibrium. Friction is the resistance to movement between two contacting surfaces. An important point to remember here is that friction always opposes motion and will always act tangent to the surfaces. So in this particular image, we have a cart being pulled one direction. Weight is pulling down. Friction will be working in the opposite direction that the cart is moving, and it will be operating tangent to the tires or wheels at the point of contact. Friction can be simply described using these two equations. For static friction, the equation is Fs equals mu s times n. Fs is the static frictional force, mu s is the coefficient of static friction, and n is the normal force. Once again, normal means perpendicular. So this coefficient becomes really important, and the coefficient varies depending on many things, including surface condition, type of surface, and temperature. The equation for kinetic friction force is the same thing, except we replace Fs and mu s with Fk and mu k respectively. In most cases, mu k, the coefficient for kinetic friction, will be less than mu s, the coefficient for static friction. And you're familiar with this from experience. It is more difficult to get a box started moving. When you say we place a box on the ground and we push against it, it's more challenging to get it moving than it is to keep it moving once we've already started. And that's because mu s, the coefficient for static friction, is larger than mu k. Many times we're concerned with something called impending motion. Impending means it's about to happen. So impending motion is the point right before the box or object begins to move. At this point, the frictional force will be its maximum, and if we exceed that, then we would move into the kinetic state. So using impending motion, we can solve for the maximum frictional force in any particular situation. There's basically two types of problems I can discuss using impending motion. The first one is slip and tip. So say we've got a large crate standing upright and we're trying to push on it, and the question is it going to slip or is it going to tip? In this case, we assume one condition, either slip or tip, and solve. Then we assume the other condition, which would be the opposite of what we assumed in the first case, and solve that. And then we compare those results and make an informed statement. It doesn't really matter if you start with the slip condition or the tip condition, which one you assume first, just that you do them both and then compare the results. Whichever one is smaller will occur first, because it would take less force to get that to occur. We can also solve problems with impending motion using no slip or tip, assuming that it won't slip or tip. We're not looking at whether the object is going to slip or tip. We are instead looking at what the actual required frictional force is to hold it in place. So the first step for that is to determine the theoretical frictional force required for static equilibrium. Then we determine the maximum frictional force that this particular situation could develop. And then we compare those results. If the required frictional force is less than or equal to the maximum frictional force, then the actual friction in that case is F rec, the required frictional force, because that situation can develop that friction. However, if the required frictional force is greater than the maximum frictional force that could be developed, then the actual frictional force is mu k times n. In this problem, you are given an object, a box that's sitting on an incline of 30 degrees, and a force of 35 pounds that's pushing against its downward tendency. The find statement asks you to look for the actual frictional force. We're also given that the coefficient of static friction is 0.2 and the coefficient of kinetic friction is 0.17. Now when you begin this problem, there's a couple of things to notice. First of all, you're being asked to solve for the actual frictional force. So that's what's actually occurring. The second thing is very closely related to that, and that is you don't know what's going on. In this situation, there's actually three possibilities. One is that the box is sliding up the incline, in which case the 35 pounds would be pushing it up the incline, friction would be acting in the downwards direction. The second case is that the 35 pounds is just enough to hold it on the incline, and so it's not moving at all. And the third case is that it's sliding down the ramp, and the 35 pounds is actually doing nothing more than preventing it from sliding down faster. In that case, the frictional force would be going up in the same direction as the 35 pounds because friction always opposes motion. Since we don't really know what's going on, the first step here is to assume the condition of static equilibrium and figure out what that frictional force would have to be in order to hold it at static equilibrium. So to start the free body diagram, I'm actually going to rotate the object 30 degrees. This is not frequently done, but in this case it's going to help. So when I draw my sign convention, I'm going to draw it rotated 30 degrees off the horizontal. After drawing my sign convention, I'll have to record all of my forces in their correct orientation. So first of all, we need our force of 35 pounds pushing against the block. Now remember that 35 pounds was parallel to the surface, and since we've rotated this, it's going to appear horizontal in this diagram. We're also going to need to apply the normal force. The normal force is always perpendicular to the surface. In this case, it will appear as vertical. We also need to draw our frictional force. We know that the frictional force opposes motion, but we don't actually know which way it's going. So I'm just going to draw it and assume a direction. And I'm going to call it F-rec. That F-rec stands for required frictional force, and this is the frictional force required to hold it at static equilibrium. Once again, we don't know which way the frictional force is going, so I've just assumed it's going towards the left. Finally, we have the weight. Be careful here because weight acts vertical, but since we've rotated this diagram, the weight is not going to be vertical. Instead, it's going to be at a 30-degree angle. Now, at this point in time, I've got all the information that I need, and I can go ahead and solve for my required frictional force. I'm actually going to solve for two things here. I'm going to solve for the value, the magnitude of the required frictional force. I'm also going to solve for its direction. And the best way to solve for that required frictional force, if we look at the x direction, there's only one unknown in the x direction, and so we can solve that using static equilibrium in the x direction. After you write your zero statement, it's very important that you're careful. And when you're doing frictional problems, I do recommend that you write all of the forces that you have in the diagram in the zero statement. Now, you can see that n has no x component in this case, but the problem that can sometimes happen is, especially when we rotate our sign convention or when we have slopes or angles, as we do many times when dealing with frictional problems, you're going to have normal forces or weights that actually have an x component. So it's important that you look at the diagram and actually analyze and say which of these forces are acting in the x direction. So px is a positive p, since p is acting in the positive direction. Wx is a negative w, and its x component is w times sine theta. F-rec, x is a negative F-rec. Solving this equation for the required frictional force gives us this, and now we can plug the numbers in. We will find that the required frictional force is a negative 15 pounds. So that tells us two things. That tells us that the frictional force we would need in this situation to hold it at static equilibrium is 15 pounds. It also tells us that that frictional force is going in the upwards direction. Since friction goes in the upwards direction and friction always opposes motion, that tells us that in this situation the box's tendency will actually be to slide down the ramp. That's an important consideration because now we need to figure out, okay, is the box actually sliding down the ramp or is it stationary? So now we're going to draw a new free body diagram with that information recorded on it. Now I'm going to draw another free body diagram, and in this case the block is impending down, which means it's just at the point of sliding down the ramp. We know that if the box is going to slide down the ramp, that we have friction acting in the opposite direction, acting up the ramp, and we also know that at the point where it's just about to slide down the ramp, the friction is at its maximum. And the maximum friction that could ever be developed by this situation is mu s times n. Now, since at this point in time we don't know if F max is actually going to be able to equal mu s times n, if we don't know if that maximum frictional force will be enough to hold it at static equilibrium, we want to solve for both n and F max, and I'll explain why later. The easiest way to solve for n is to apply static equilibrium into the y direction. Now you'll notice that a number of these forces do not have y components. P does not have a y component, and F max does not have a y component. I was talking with you about common mistakes earlier. A common mistake in a friction problem is to assume that N equals W, the normal force is equal to the weight. That is only true if the normal force and the weight are acting on exactly the same line of action. In this case, since the block was at an incline, the normal force equals a component of the weight. Solving for n, now I can plug the numbers in, and we'll find that n equals a positive 86.6025 pounds. So now that we see what n equals, we want to solve for F max. So F max equals mu s times n. And we'll find that F max is 17.3205 pounds. Our last step is comparing the required frictional force and the maximum frictional force. We found that Frec is 15 pounds. Remember, Frec is the required force to hold the object at static equilibrium. We just solved for F max, and it is 17.32 pounds. Since the required frictional force is less than or equal to the maximum frictional force, we know that Fa, where I'm calling Fa the actual frictional force, is equal to 15 pounds, the required frictional force. Basically what we're saying is the maximum frictional force that could ever be developed by this situation is 17.32 pounds. As long as the frictional force required to hold it at static equilibrium is less than that, then that required frictional force is actually what the friction being applied to this situation is. If this wasn't the case, if the required frictional force was greater than the maximum frictional force that could be developed in this situation, then the box is moving. And if the box is moving, the actual frictional force would equal mu k times n. This is the reason why I solved for n over here, because at the beginning of this problem I didn't know if the object was moving or not. So it's helpful to solve for n first, so that if we find out the box is moving, we can just plug in Fa equals mu k times n and solve it. If I would have solved for F max directly using some of the forces in the x direction, I could have still done the comparison. But if I got to the end and I saw that it was greater, then I would have had to go back and solve for n. So in the answer box, I put the actual frictional force Fa equals 15 pounds going up at 30 degrees. In this case, I have included the sign as a vector symbol so that there's no confusion as to which way it's actually going.